And this is the Unit 10 seminar on types of asymptotes. At this point, all you have really learned through the MCR course is how to identify vertical asymptotes, which I'm going to review again. We never really talked about horizontal asymptotes. However, in this unit, because you are going to have to deal with, we learned in Unit 9 synthetic division for large degree polynomials, and we're going to continue that, except now you have rational functions where you will have an nth degree polynomial, so anything higher than the power of 1, in the numerator as well as the denominator. And we're always concerned about the leading coefficient, or the degree of attached to the leading coefficient, the highest basically exponent in the polynomial. And that's why it says ... here, because it doesn't matter how many. You could have x to the power of 5 plus x to the power of 4 plus x to the power of 3, but I'm only concerned with the highest degree, the nth degree polynomial, in both the numerator and the denominator. And that will indicate what type of horizontal asymptote you're going to generate. Now, I'm going to come back to this slide. We're going to break down points 1, 2, 3 in depth with examples. But first of all, I just want to look at vertical asymptotes. So please copy the definition, because we really touched on this a little bit in grade 11, but now I really want to make sure you know exactly how to identify vertical asymptotes. So to find a vertical asymptote, you have to set the denominator equal to 0 and solve for x. If this value, which we will call a, is not a removable discontinuity, then x is equal to a is a vertical asymptote. So, for example, if notice I have a polynomial on the top and a polynomial equation on the bottom. First thing I'm going to do is factor both my numerator as well as my denominator. Let me give you very simple. The denominator is a difference of squares situation. And you will notice that the denominator always corresponds to the vertical asymptote. So if I factor that denominator, I will have x plus 1, x minus 1. And my numerator is going to be x minus 4, x minus 1. So you will notice that there is going to be vertical asymptotes. First, when I cancel out my x minus 1 and my x minus 1, I'm left with x minus 4 over x plus 1. That's my final function. However, you will remember last year, I said to set them equal to 0, everything in your denominator. So if I set x plus 1 equal to 0, I know x plus 1 cannot be equal to 0, because otherwise our function is going to be undefined at that point. So that means x cannot be equal to negative 1. And then we have x minus 1 cannot be equal to 0. X cannot be equal to positive 1. So that's what you would do last year, state the restrictions, and the restrictions corresponded to vertical asymptotes. But now we're going to go one step further with this definition of the removable discontinuity. When you can factor out a term in the numerator and factor out the same term in the denominator, thus canceling each other out. So when we transformed our equation into factored form, what cancels out here? What cancels out? Yes, x minus 1. So that means that x minus 1 is our removable discontinuity. So at the point x is equal to 1, this is going to be my removable discontinuity. That leaves me with my vertical asymptote. The only vertical asymptote that I have would be x cannot be equal to -1, so the equation of the line is x is equal to -1. That is my vertical asymptote. I kind of disregard the x minus 1, or x is equal to +1, because it cancels out in both the numerator and the denominator. So that's not my vertical asymptote. My real vertical asymptote is going to be at x is equal to -1, which corresponds to the denominator of my final answer. These are both restrictions, right? The function is not defined at, or the function is not, there is no function at both of these points. There's no value. However, the vertical asymptote is the only one that doesn't correspond to a removable discontinuity. In your notes, I would like you to copy down examples of removable discontinuity. So the function exists at all points except at, in this case, the point +1. There is a hole there. So that's really what a removable discontinuity looks like. These are two examples of it. So the value of the function is not going to be defined at that particular point. Oops. Now in calculus, you're going to go through these concepts as well. Do not confuse removable discontinuity with the picture that I have underneath here. We keep going down. So it lets me go down. Picture that I have on this side, at the function, the function actually jumps. It still has a discontinuity, but it jumps and to another value. This is called a jump discontinuity. So do not confuse removable discontinuity with jump discontinuity. This you don't really encounter in Unit 10, but you will encounter later in the course, as well as especially in the calculus course, okay? So I need you to be able to identify the difference. So that's really all we have for vertical asymptotes. Vertical asymptotes, removable discontinuities, and remember, vertical asymptotes are always attached to the domain because its x cannot be equal to x values. Now we have to talk about horizontal asymptotes. So this happens, point number 3. If the degree of the numerator is higher than the degree of the denominator. So any example with, let's see, in this case there are no horizontal asymptotes. So if we have x cubed minus x squared plus 5 over x squared minus 4, the degree of the numerator is higher than the degree of the denominator. Then no horizontal asymptote, there is no horizontal asymptote. What is going to take place in this situation is going to be a slant asymptote. So there is no horizontal asymptote, but there is something called a slant asymptote, which is the most complicated part of the unit, which I'm going to do a couple of questions at the very end on slant asymptotes. But that's the first thing. Whenever you notice that the degree of the numerator is higher, you should be able to say that there is no horizontal asymptote right away. The second situation we have is if the degree of the numerator is less than the degree of the denominator. So situation number 1 on my first slide, then there will always be a horizontal asymptote. So a case like this, the degree of the numerator is less than the degree of the denominator. My horizontal asymptote, this is usually the case, horizontal asymptote is just going to be the y-axis, so y is equal to 0 would be the horizontal asymptote. So usually when the degree of the numerator is less than the degree of the denominator, we always have the y-axis as the horizontal asymptote. If we have a number actually associated with our horizontal asymptote, it's usually because the degree of the numerator is the same as the degree of the denominator. In this particular case, you are going to take the numbers in front of the leading coefficient, so my A term and my B term, and our horizontal asymptote in this particular case would just be y is equal to 3 over 2. Whatever your A term, the leading coefficient of the numerator is, over the leading coefficient of the denominator. In this particular case, because I have 1 over 1, my horizontal asymptote would be just y is equal to 1. So whenever you have a number associated with the horizontal asymptote, y is equal to -5, y is equal to positive 3 over 2. It's usually because the degree of the numerator is the same as the degree of the denominator. Those two scenarios is where we have actual values associated with a horizontal asymptote that exists. Does everyone understand that? So very straightforward. There's no complicated math involved. It's just knowing the rules and knowing when to identify the horizontal asymptote. Now, slant asymptotes are the more complicated topic, and the first piece of information to recognize a slant asymptote, and I'm going to give you a few minutes to copy this because this is a brand new topic, and this is what a slant asymptote looks like. It's usually a linear function, rising or falling, linear function, slanted line. So our slant asymptote is always going to be a linear function in the form y is equal to mx plus b. It occurs when the polynomial in the numerator is a higher degree than the polynomial in the denominator. It's also called the oblique asymptote. They might refer to this in your textbook as an oblique asymptote. And to find the slant asymptote, the reason why I'm teaching this to you before synthetic division in Unit 9 is you have to divide the numerator by the denominator using either long division or synthetic division. So I'm going to do the first one with you, and then we're going to do another 2 questions on your own, but we'll check your answers with my answers, okay? I'll give you a second to copy that down. Okay, so let's actually do the synthetic division for this one. So, I'm going to do long division actually. So x plus 5, and then we have x squared minus 6x plus 7. Okay, so I know that x plus 5, I'm going to first focus on my x squared minus 6x. I know that that will go into x squared minus 6x, just x times. When I multiply that, x times x is x squared. Positive 5 times x is a positive 5x. When we subtract those two things, I get negative 6x minus 5x, which is a negative 11x. I have to bring down my positive 7. So x plus 5 can go into negative 11x plus 7. If I say negative 11 times, I have negative 11x minus 55. So It's not an exact value. I have a remainder for this particular question, but that's okay. My equation of my slant asymptote, I don't have to go and continue solving because there will be a remainder, but approximately that line that I drew, x minus 11. Y is equal to x minus 11 would be my slant asymptote. It's a linear function. So I want you to give me approximate values for the following two questions, and this is the end of our seminar. So you're going to do long division for 2x plus 6 goes into 3x squared plus x minus 2, and 5x cubed minus 8 divided by x squared plus 3x minus 1. So try that on your own. And they're approximate. They don't have to be exact. I'm not looking for remainders. Well, this one's a little bit tricky. 2x plus 6, let me do this one with you. Because that 2 can be factored out, it actually only goes into 3x squared plus x. We would do 3 over 2 would be my slope of this line. 3 over 2x. When you multiply that, you get 3x squared plus 9x. Subtract those equations, you get negative x minus 2, which would give me negative 4 can go into negative 8x, 2x plus 6 can go into negative 8x minus 2 about negative 4 times. So this becomes negative, positive 8x minus 24. So that means my slant asymptote in this case has a slope of 3 over 2x minus 4. And then this is good review of Unit 9 concepts. So right away you know long division is going to be a huge part of, or synthetic division will be your huge part of your Unit 9 test. Sorry. Now so let's do one more question. Raise your hand if you still need a Unit 9 seminar in here. Okay.
Was that the one about the intro to asymptotes?
No. But I'm going to do one right after this. Okay? So x squared plus 3x minus 1. And now I have to, now this is a little bit tricky, 5x cubed minus 8. So notice 5x cubed, but I don't have a term for x squared, so I'm going to say 0x squared plus 0x minus 8. This is the best way to really work with this type of equation. So this time I'm going to be focusing on the first three. X squared can go into basically 5x cubed 5x times. And when we do that, we might have to extend the page. When you multiply 5x times x squared plus 3x minus 1, you're going to get 5x cubed plus 15x squared plus 5x. But remember, you have to subtract these two equations, so that positive 15x squared will become a negative 15x squared, positive 5x minus 8. And again, we're really only focusing on the leading term. So x squared plus 3x can go into this negative 15 times. That's how I would get negative 15x squared, and so on. So my asymptote is approximately going to be equal to the equation y is equal to 5x minus 15. So the leading terms are very important. Now, Unit 10, because these are approximate slant asymptotes, you don't have to go all the way. You really, if it doesn't divide completely, if there's going to be some wacky remainder that has nothing to do with the asymptote, these are approximate values. However, for the Unit 9 material, you will have to finish the question completely, okay? So, let me just stop recording this.